This is CS480 Autonomous Robots. In our group we have Jamie Cranbeck and Eric Smith and me, Kayla Funky. Our project was about teaching the Turtlebot how to detect mines while mapping a minefield, or in this case just the robotics lab. For the purpose of our simulation, we are using this orange trick-or-treat pumpkin as our mine. We use the G-mapping package available with the Turtlebot to map the environment, as well as OpenCV to deal with our classic computer vision problem of how to detect objects. We picked the project so that we could simulate the real-world problem of removing unexploded landmines and their ordnance left over from past wars. As you can see, our robot is now randomly wandering around, and we have a mine over here on the right side of the island, and our second mine is hidden in the corner over here. The Turtlebot is able to recognize landmines by first creating a histogram of the hue and saturation of the pumpkin. It then compares this control histogram to those calculated from the images coming in from the Kinect camera and searches for matches. It can then calculate the center point of the pumpkin in the 2D image using a class written by our professor, Nathan Sprague, called Blob Finder, and this uses CV contours. It converts the center point to an XYZ 3D point in the camera coordinate frame so that we can view it in actual space. It publishes all the pumpkins it currently sees as a marker array to a topic so that you can pull it up in RViz and view it in relation to the robot. Another node we created is listening to this marker topic and determining whether the currently displayed mine or mines are new, in which case it'll be added to the collection of mines, or if it's just a previous mine that's being viewed from a different angle. Whenever we're ready, we can tell this node to create a picture of the current map and draw the locations of the mines on it as red circles. So our final product is a picture of the map with the mines clearly marked on it.
Before I talk about some of the challenges we encountered, here are some shots of the screen during operation. On the right, of course, is RViz displaying the position of the base of the Turtlebot and the current state of its map, including the position of a mine it encountered, which is shown here by a red dot. The terminal window on the left shows the output of the Mark Mine node, which outputs the coordinates of the mines the Minesweeper sees. This is the output of the Map Marker node. It contains basic information about the current mine in question, as well as information about the existing collection of mines. Add false, for example, indicates that the system has already encountered a mine in this position, and therefore the Map Marker node will not add it to the collection. Finally, here's an example of a simple map output by our Minesweeper system. One of the main challenges in the project was actually just using the OpenCV library. Computer vision wasn't something that anyone in our group had any experience with, so there was already a learning curve associated with understanding the use of things like histograms and back projection. But when we were ready to start writing code and applying what we learned, we found the OpenCV documentation to be hit or miss. It was usually vague in areas in which we needed clarity, and especially in the sections concerning use of the library with Python. It's probably safe to assume that dealing with hardware problems is common in robotics, but this was a constant struggle for our group. The Minesweeper relies on successful interaction between a mobile base, a Kinect, and a netbook running our code. Often when unpredictable errors occurred, it was impossible to discover the cause. We would either have to restart everything or start again with another Turtlebot. In addition, the performance of the netbooks would often suffer, which made testing strained. In many cases, technical difficulties were often the only thing stifling progress.
In the future, we want our robot to be smarter about how it chooses to wander its current area. Currently, it will move forward until 1 meter away from any obstacle it detects. Then, it will rotate a random number of degrees and move forward again until another obstacle is detected. We want our robot to prefer to go to places it has not already mapped. This makes map creation more efficient. Another plan we have for the future is to incorporate the use of multiple robots that would share information over a network.